everybody.
Milk's here.
And MoNaCo.
PBOM, this is something like video 5.
3 pages of notes in our packet dealing with heat associated with the cooling and heating and phase changes of water specifically.
Right, so we went over these, the heating and cooling curves. We changed temperature and phase.
Yep.
And now today is how much heat's involved.
Right, we want to put a number. How much heat, how many joules are involved in this change in temperature or this change in...
About time for just a little bit of math.
A little bit of math, mostly plug and chug, but you got to know when and how to use each
That's
problem.
the key to this video.
And we like to give you background information about calorimetry and calorimeters. What are these things?
Well, calorimetry is basically just the measurement of heat in a substance.
Okay, it's
So
the
that's
act of
stored
process.
energy, yeah.
Uh-huh.
And then the calorimeter is that specific piece that helps me detect that.
That's your tool.
That's my tool.
And I'll show you all a little demo of this kind of thing. It's like we use calorimeters and calorimetry to decide how many calories are in our food. So you take your Big Mac and you burn it, combust it all the way. When that happens, it releases heat, which they use to heat up water. And then depending on the change in temperature of that water, you can work back through the equations we're about to show you and decide, oh, that Big Mac had 1 billion calories in it.
Right.
And you shouldn't eat more than one a year.
Right. The key with how those things work is how do I take all that heat I generated and make sure it goes just into the water?
So yeah, there's
It's
always
very
going to be a
specific.
% error. That's why we don't really do this as a lab because the results are not repeatable.
What we do is we use these equations we find in table T, the last page of the packet, or I'm sorry, of your reference tables.
Yeah.
First equation.
Q equals MC delta T, or QMCAT.
Right. I say MCAT.
Yeah. Your key word here is the delta T, or the key term here is the delta T. You got to use this equation whenever your problem is having a temperature change.
Right, so that's going to probably be on the slanted piece.
Remember,
Our temperature does not change during phase changes.
So we have to have other equations for those phase change temperatures.
Specifically, Q equals MH delta F.
Q and a half, not delta F. Q
I didn't say delta that time.
Yes, you did.
Oh, I specifically said don't say delta.
I did, but
All right,
now
don't say delta, Milks.
don't say delta F. It's Q
just
M
HF.
H subscript F, or MHF.
Yeah, man. So we use this. The F stands for fusion.
And H stands for heat. So the F is subscripted because it's the joules equals the mass times the heat of fusion.
Correct.
Right. So fusion or melting, it happens when we're doing from like a solid to a liquid or
A liquid to a solid.
those are your keywords there.
And will generally be at, for water, 0 degrees Celsius.
Right, another key word and a key number. So you use that equation when your problem's got 0 degrees Celsius and that phase change.
Correct. That's what
Last one, let's try it this time.
All right, ready? Q equals MH subscript V.
Yeah.
Oh, I so didn't say it this
I know. So this we use for vaporization. V, vaporization. F, fusion, freezing, vaporization. They're different phase transitions that require different amounts of heat. So we have different equations and constants to run them.
Right, and it doesn't matter if I'm heating or cooling. If I was cooling, this would be the condensation point.
Right.
Which is the same point as the vaporization point.
Right. So there are your equations. So let's break them down as to what these C's, HFs, and HVs mean.
Sure. Now on the front page, of course, they couldn't put it all on the same page.
Never.
Never. The front page, table B says C, the heat capacity of water is 4.18 joules per gram Kelvin.
Right. What's that mean, boss?
That means I need to add 4.18 joules to 1 cubic centimeter or 1 milliliter of water, 1 gram of water to change it 1 degree Kelvin.
Period. End of story. Now, do you think that's the same number for all stuff out there?
That one is very specific to water.
Right.
And it does some cool things. We live by the lake.
Yeah.
So that's kind of the reason why the lake will stay kind of cool the air in the beginning of summer when it gets hot out, or vice versa.
Our students don't have a reference for this. This is actually a very high number for a specific heat capacity. You wouldn't know that just by looking at that. But
everything else
materials is usually much, much lower.
Like 4 times less.
Right. And the better an insulator something is, the higher its specific heat capacity would be. Because think about it. You want insulation. You don't want your temperature to change very much.
When I add a little bit of heat.
Right. So if you got to have a specific heat capacity that's very large, means you change temperature very slowly and very reluctantly. Perfect for insulation in a home or something like that.
Sure.
Yep. So that's what specific heat capacity means. C for water.
And that's in the MCAT formula.
Yeah, only
Right.
one that we use that for.
And H sub F specifically has a number.
This is the heat of fusion for water again. This means that you have to add 334 joules to 1 gram of water to get it to change from a solid to a liquid. Or you have to release 334 joules of energy from 1 gram of water to get it from change from a liquid down into a solid.
There you go. But in that particular phase change, these are the amount of joules
And
required.
this is specifically for water, so if this was something else, it would have a different
And
value.
they'd have to give it to you.
And you'd have to be given it. I've never seen it. These are specifically for water.
Sure.
Always remember that.
Right. And the table does say that too. Table B does say physical
For
constants
water.
for water. Now vaporization, it takes a lot to go from the liquid phase to the gas phase. To take us to vapor, it takes a lot more heat. 2,260 joules per gram.
Right. So if you had 10 grams, you'd multiply by 10. 100 grams, multiply by 100, and vice versa. If you're a gas and coming back down into a liquid, you're going to release a lot of energy in the process. So that's what these constants are kind of related to. Let's see how we work and use with these all together.
Okay. So first we're going to do the heating cooling curve.
Mm-hmm.
So first, a heating curve is going to look like this.
And you got to know when to use which.
Yeah, where am I on the heating curve when I need to use this?
Right.
So
Just
let's label up. Yep. We'll label this guy up. So the first equation we're going to look at is the MCAT. Now remember, the MCAT we use specifically when the temperature is changing. And looking at this curve, I see 3 spots where the temperature is changing.
When you have a solid present. When you have just a liquid present.
And when I have just a gas. So remember, these equations are going to give you some sort of change in temperature of some sort.
You're going to know.
Right, so H sub F.
Right.
I'm going to use that specifically only at the freezing point. So solid to liquid or liquid to solid. Because the freezing point is the same for both.
Mm-hmm.
And H sub V will specifically be at the vaporization point or the boiling point, condensation point. Okay?
That's it.
Good.
Yeah.
Well, guess what? Same thing with the heating curves and the cooling curves are exactly the opposite.
Right.
So we're going to go through this pretty fast. We can label it up with our stuff. But again, MCAT is going to be where there's a change in temperature. So that is going to be our slanted lines, where I'm just solid, where I'm just liquid, and where I'm just gas.
Booyah.
H sub F is heat of fusion, so that's where I'm going to be the freezing, liquid going to solid or solid going to liquid.
And that's kind of weird because F stands for freezing, so you think liquid goes to solid, but F really stands for fusion, which is both. It's kind of like...
Yeah, and it's really associated with the melting, which is always confusing.
Right, fusion is another fancy word for melting, so it messes you up, but just remember F freezing, liquid to solid, and the reverse,
Right.
solid to liquid, the melting itself.
Right. And if you forget, H sub V is pretty obvious that that's vaporization. So we can always go by what we know, what the obvious is, and backtrack from there,
Opposite of vaporization is condensation,
which also happens at this point.
same temperature.
Okay, correct.
Cool.
For water.
Good job.
Good. So heat flow. Really?
Example heat flow calculation with QMCAT.
Yep. I had 100 grams of water, and the heat is heated from 20 degrees Celsius to 75 degrees Celsius. And now it's a matter of plug and chug. I'm going to plug in my M, my C, and my delta T.
So, let's see.
The mass is 100 grams.
100 grams.
4.18 is our constant, and we have a change in temperature, which is 75 minus 20, which is going to be 55 degrees.
Okay. And so when you plug this through in the calculator, you'll get your answer. Do it.
Right. 100 times 4.18 times 55.
You do that, put a box around your answer, and bang, 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 so you know. Chug it.
And if you follow the units, you're going to see the C's cancel and the grams cancel, and I'm left with just joules.
We like boxes around our answer, so do it. Plug it, chug it, do it.
Do it. And then here's the good one. So calculating the change, if I only if I want to know what like the final temperature is.
Right.
Okay, so I got 100 joules of heat. This time it's given. I have a 100-gram sample. I'm going to start at 25 degrees. So I'm just going to solve for delta T now. So it's going to be 1,000 joules equals 100 grams times 4.18 times delta T.
Times delta T.
Solve for delta T.
Right, so delta T equals
a number. And then delta T is always going to equal the, right, and now delta T is going to equal the final temperature minus the initial temperature.
Right, so you mean there's another little tiny step?
There's another step here.
Because we added heat to water at 25 degrees. So whatever this delta T was is how much the temperature is going to change by.
Correct.
Because remember, delta T in general equals T final minus T initial. And we know T initial was
25.
We know what delta T is equals X in this case. You'll take your delta T from there minus
25 degrees.
25, and that's how you'll know what your final temperature was if you solve for X.
Right.
A little logic will help you along the way there.
Right. This is about the most complex of a problem we could get.
Right.
A little extra step to the plug and chug.
Yeah, for sure. So let's see what else we got.
Okay. So, just for phases. Okay.
Sure.
So how much heat is absorbed to melt a sample of water at a given mass? Melt being the key word.
Yep.
That phase change is associated with H delta F.
Mm-hmm.
And so the problem would read like this. How much heat is absorbed to melt 50 grams of ice at 0 degrees Celsius?
Right. Q equals M times H F. And then I'm going to plug.
50 grams.
50 grams.
And H sub F is?
334 joules per gram at 0 degrees. That's the fusion, so I would plug it.
Grams cancel. I'm left in joules.
Use our answer is joules. Put a box around it. You got your little calculation. Do it yourself. Find your online calculator if you got to.
Right. Next one. How much heat is released to freeze a sample? Freezing, that one's easy. H sub F again.
Yep.
So, sample problem. How much heat is released when 60 grams of liquid is frozen at 0 degrees Celsius?
Now, you might notice I'm writing the equation over again. That's my own neuroses. Always got to do it. So, Q equals 60.0 grams times. This is frozen, freezing.
It's still
334.
Correct, because I'm still at that same spot. The answer again will be in joules. You plug and chug it. Well, we actually plugged it, so you chug it.
Yes.
There you go. Okay, so heat absorbed, vaporized, V. Lets me know I need a different equation.
Yeah.
See how that works? So now I got H sub V. The problem would say something like this. How much energy absorbed to vaporize 19 grams of liquid water at 100 degrees Celsius?
Now notice I'm using 2260 joules per gram.
Because that's H sub V and not H sub F.
Right.
The problem's going to tell us which one to use.
Mm-hmm. With the keywords. It's not going to specifically say
Correct.
use this equation. It's
You're
going
right.
to say vaporize,
Right,
freeze,
but it's hidden
melt.
in the problem.
Yes.
We need to be able to diagnose it. So condense happens at the vaporization point. So condensation happens at the vaporization point. I use H sub V. How much energy is released with 70 grams of water is vaporized, vapor is condensed at 100 degrees Celsius. I plug in the 70. Again, I'm going to use H sub V, which is 2260. Grams is going to cancel, and I am left with some number of joules.
Mm-hmm.
We plugged it in, you're chugging it out.
Yep.
And those are all the kinds of equations we could possibly see.
There's one that we didn't do, but we're going to do plenty of it in class, is find the mass.
Okay.
You
Right.
know, but that's algebra.
It's still just plug and chug.
Right, exactly.
still just
They'll
plug
tell
and
you
chug.
how much heat and how much, what phase transition, how much was the sample,
Sure.
how much did it weigh.
A lot of times they do those particular problems if they're going to do a different substance other than water, and they give you
Right.
the new H sub
That's
F
true.
or the H sub V.
But I think all the examples we put in our practice are dealing with water.
Yeah, because that's mostly what we're going to see. But you
Mhm.
need to be able to change gears if you have to.
Lots of practice, lots of math, so those of you who've been waiting for some of it, this is real good math for chemistry.
Yep. We need to be able to know which heat equation to use when.
Very much so.
We need to know where our physical constants are.
Yep.
And where do and how do I solve heat problems?
For joules, mass, and delta T. It's algebra.
It's just algebra. Plug and chug.
It's algebra.
If there's three,
Solve for X.
if there's 3 variables, they're going to give you 2.
Mm-hmm. And
Right.
have you find the third. The hardest scenario would be when you're finding the final temperature, and you have to remember that, okay, you got to look for the heat added or heat removed and decide if you got to subtract or add to your initial temperature.
All right. Hey, thanks for watching, guys.
Thanks all.